Hey guys, welcome to another video. So today, another question from the Nice Question series in the Extension 2 syllabus. Today's question comes from North Sydney Girls, 2023, last question in their trial paper. So meant to be a little bit hard, a little bit tricky, but lovely. Actually, it's not that bad. So I thought I'd share it with you. Now, before I go on, if you haven't already done so, please like the video, subscribe to the channel, and tell your friends. Guys, let's get stuck in. So today's question, North Sydney Girls, 2023 integration, looks like this, right? 5 marks to conclude their paper. So let's get stuck into this. So they give you an expression for the E constant, right? Which is a sum of fractions of factorials. Great. Okay. Question 1. Use a binomial theorem to show that inequality. Great. And then part 2, given that this px or pn function looks like that, right? Using the AMGM inequality, show that the function is less than E. Okay. Let's do this, right? So the first question tells you to use binomial theorem. So let's use binomial theorem. So part 1, right? So I have the binomial expression looking like that. Now I know if I was to use binomial theorem, it'll be like NC0 1. Is it 1 to the power of n? Yep. 1 to the power of n and plus NC1 1 to the power of n minus 1 times 1 on n1 plus, yeah, I'm just going to establish the pattern m squared plus, now the general term, which I actually care about, right, is m1 to the power of n minus k, and then that's 1 on nk, and then last term n no more n's, no more one, sorry. And so basically what that is n0 n1 1 on n plus n2 1 on n squared all the way to I'll put in the general term. Yeah, put in the general term. Okay, then last one. Yeah, just to visualize, right? Just to visualize what I want to do with this. All right, now, if that's the expansion, right, using binomial theorem, I'm going to try to, let's explore the general term, right? Yeah, maybe because the question itself has factorials. I'm assuming they expanded this somewhat, right? So let's do this. So that's like n factorial, k factorial, top factorial, bottom factorial, top minus bottom factorial, and then multiplied by 1 on n k, I guess. Yeah. All right. So once you get that now, let's see, what can I do to this? So it looks like what I will do is I'm going to do 3 things, I'd say. 3 things. 1, I'm going to put this guy, and I'm going to expand it. Right, I'm going to put these 2 together. I'm going to pull out the 1 and the k factorial, and then I'm going to break this guy up. All right, I'll show you what I mean. So 1 on k factorial there, right, in front. That's actually quite important, probably the most important part. Now, for this n, I'll do it in a few steps, right? So actually, I'll leave the pink untouched now. This guy here, you guys know that when you take a factorial, well, let's say, for example, if I take 6 factorial and I divide by 6 minus 2 factorial, right? So let n be 6 and k be that. That equals to what? 6 factorial over 4 factorial, which is just 6 times 5, right? Yeah. So when you do similar things, so let me park this theory over here. When you do similar things to like n factorial over n minus k factorial, basically the n minus k factorial part cancels out, right? And you sort of get like n times n minus 1 all the way down to n minus k and n minus k plus 1. Is that right? Plus 1, yeah? Because the n minus k bits thereafter go away. So I'm going to break this into n times n minus 1 times all the way down to n minus k plus 1. Now, how many terms are there? Yeah, let's see. So I think there's k terms, right? Just to be clear, because n minus k, I think there's k terms. Yeah, and because the n power k also has k terms, right, I'm going to do something spectacular, right? And just to be clear, so now I'll delete this, I'll show you. So I'll retain this theory over here, right, as the top part. And for the bottom part, we know that obviously n to the power k is equal to n times n, yeah, k times, right? Yeah. So what I'm going to do is then break this up, right? Where I'm going to basically, you know what? I'll copy this black part. Copy that black part. Cut it. Copy it. And then I'm just going to do one more step before I do the step that I really want to show you, right? So on the bottom, it'd be n times n times dot 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 n, right? I'm going to break up the fraction. Right, so it'll be like 1 on k factorial times n on n times n minus 1 on n times dot 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 times n minus k plus 1 on n. That's important. Why is that important? Because that's important. Now, looking back up, sorry, won't look out. And that's important because, guys, right now I've got this whole general term of this pink part here equal to k on 1 on k factorial multiplied by a string of these other fractions. Now, what's important is that if you take this, now this guy's obviously 1, but if you take this, right, n minus 1 on n, that's definitely less than 1. All of these are smaller than 1, right? Yeah. So therefore, if I'm multiplying the pink term by terms that are smaller than 1, this whole expression has to be less than 1 on k factorial, right? Yeah. Pink multiplied by things that are smaller than 1 has to be smaller than pink, right? Does that make sense? So once I get that, right, I can conclude that this string of binomial products here, right, each one, so for example, this one here, right, is less than 1 on k, right? So k is on the bottom, right? So this one here is less than 1 on 0 factorial. This one here, right, is less than 1 on 1 factorial. This one here is less than 1 on 2 factorial. Obviously, the k one is less than 1 on k factorial, right? Plus dot, dot, dot. And the last one there is less than 1 on n factorial, right? Yeah, which I know, right, looks to be the expression for E now. Scrolling back up, what is E? E is defined as 1 all the way to R and continuing thereon. Now, this guy is your 1, right? That's the first term. So I actually have it less than. Now, because my expression here actually concludes at n, it has to be smaller than E, right? So this has to be definitely smaller than E itself, yeah? Because that's 1, and I conclude at n while they continue on indefinitely, right? So done it, right? So therefore, right? So maybe I'll put a little space for conclusion. So therefore, maybe I'll do like this. Therefore, 1 plus 1 on n to the power of n less than E. It's nice, right? So just play that back, right? So basically, I used binomial expansion so you get an expression, but I was sure, so I was quite certain that I would do something with the general term. So breaking down the general term, right, I split into sort of 3 parts. I isolated the green part, right, 1 on k factorial. For the blue part, right, we can actually net those off, right, to leave only this bit here, right? And then the denominator, right, split into multiple n terms. And then we basically split that fraction up. And because each one of those, or some of those fractions, excluding the first one, all of the fractions are less than 1, pink times anything that's less than 1 is going to be less than pink. Great. So then the general term is less than 1 on k factorial. So then for each one of these other terms in the binomial expansion, put them in, and you can see visually that that is less than e, because e is the same expression, but it goes on forever, right? Done. Guys, the binomial expression is less than e. Wow. Okay, that's nice. Now, that's 2 marks, right? Let's have a look at part 2. So let me delete this. Cool beans. All right, now part 2, what's it saying? So I got this expression, right? Got this expression using inequality, okay? That now, the best way to do the next part is that because they define Pn to be, now what's important here is all these expressions are multiplicative, right? It's a product, which sort of looks like, if I use this inequality, it looks like this bit, right? It looks like this bit. So actually, before I do that, maybe I'll get rid of the nth root. So I go x1, x2, x3, all the way to, oops, xn is, now that's on that, so it'll be less than or equal to 1, 2, all the way to xn on n to the power of n, right? Yeah, because then I'm just going to sub this guy into here. Now, before you do that, I just want you to see, right, what's special about these terms. Let me get rid of the x's because they're a bit distracting, right? What's special about these terms, right? Yeah, each one of these, right, follow this pattern here. And this pattern, just to be clear, can be split into like, if you split the fraction, 1 on 2n, right? So for example, this guy here is the same as like 1 plus 1 on 2 to the power of 0, 2 to the power of 1. Yeah, perfect, 1.5. Yeah, this guy here is going to be 1 plus 1 on 2 to the power of 2. Yeah, quarter, perfect. Yeah. So that's the pattern, right? That basically resides within that string of numbers. So we're going to try to use that pattern and sub it in here and see where it takes us, right? So for example, right, I know that Pn currently equals to 3 on 2 times 5 on 4 times all the way to 2n plus 1 on 2n, right? Yeah. So now I'm going to basically put this into, and I say this is less than or equal to, right? In terms of the inequality, less than or equal to this guy, right? So let's say I'll just put it, all the x, so this is like x1, this is like x2, and this is xn, right? Yeah, put it into the formula, and I get 3 on, ooh, wrong color for some reason, 3 on 2 plus 5 on 4 plus all the way to 2n plus 1, 2n, all over n, power n. Is that okay so far? Yeah? Is that all right? All right. Now, once I get that, I am going to simplify this a bit. Now, I'll take out the 1 on n, right? Sorry, take out the 1 on n. And then for each one of these, right, I'm going to do that pattern thing that I was talking about, right? It's like 1 plus. Now, I'm going to basically decompose that into, so for the 3 on 2, I'm going to call that 1 plus 1 on 2. For the 5 on 4, 1 plus 2 to, sorry, 1 plus 1 on 2 to the power of 2 plus 1 plus 1 on 2 to the power of n, right? Yeah, is that right? Sorry, I didn't need that fraction. You know what? I'll do this first, right, before I do anything. Yeah, just to keep it simple, right? Keep it simple and visual. Okay, that one there. I'll still put all over n. Yeah, and I'll bracket it up n. Yep, perfect. Now, we're going to split the top, right? Take out all the ones, and you sort of see, right? There's how many terms are there? There's n terms, right? Yeah, so when I do this, it'll be like 1 plus 1 plus 1, n times, right? Yeah, there's like n terms. Yeah. So take out all the ones from all these bits here, and then for the rest of it, it's set up nicely with something that looks a little bit like a GP, doesn't it? Half plus half squared all the way to half to the power of n. Right, let me just check that in terms of, yeah, that's perfect. All over n. Yeah, to the power of n. All right. Now let's see where that takes me, right? So let's see. So I got, now that's obviously, so maybe I'll go 1 on n plus, now that's a GP, right? So that's a GP where a is a half, r is a half, and n, right? N is n, right? So it'd be a times r to the power of n, or do the 1 minus because r is half, right? So 1 minus half to the power of n over 1 minus r. Yeah. 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 All right. Now, that looks like half cancels out with half. Is that right? Yeah. So this bit here looks like it cancels out with the bottom because that's half. And then I sort of get like a situation that looks like, okay, let's see. 1 on n times n plus 1 minus a half power n. n. All right. Now how much space do I have? Not much. Okay. Can I just go up here, guys? Yeah. So let me just copy this, just so I can visually see it. Oh, it's all grouped. Okay. Just gonna move it up here. Now, how can I clean this up? So let's see. I'm gonna maybe expand that. Because when I expand, I get 1 plus 1 on n minus, now what's that look like? 1 on n, 1 on n to the power of n. Now, if that's what it equals to, because n are integers, right? Yeah, are we given n as integers? Well, I guess they are, right? Because it's part of the binomial theorem where n is not only that, it's positive integers, right? Yeah, so then this has to be negative, right? So that's the fraction's positive, but when I minus it, it'll be like small, right? So this guy here has to be, oh, sorry, maybe just highlight this guy. Yeah, they're all integers, n's integers, so that must be greater than 0. Yeah, positive integers. So therefore, this is equal to 1 plus 1 on n to the power, oh, sorry. Because this guy's greater than 0 and I'm minusing it, this whole expression has to be less than 1 minus 1 on n, which I know is less than e from part A. And then I'm done, right? Therefore, right, Pn, which was less than or equal to this expression, and this expression is less than this piece, it's less than e, I can conclude that P of n is less than e. That's nice. Guys, how was that question, right? It's a nice question just to close out the North Sydney Girls paper. I thought it was a nice one to bring to you guys because as to deal with proofs and inequalities, sometimes when you look at these questions, right, the facts are all given to you, all in the blue. You just gotta try to use it, use a bit of manipulation of the algebra. So the concept here is that when you're proving, especially in 4-unit maths, if you're proving something is less than something, right? So for example, if you were proving A is less than B, right? Sometimes what you have to prove is that A is less than, now in this case, you can sort of see, right? It's less than and how should I put it? Less than B. So that's B there. So it's less than B. If you can get a less than B minus, like, let's say 4. Yeah. If A, was it? Let's see if A is less than that, then that must be less than B, right? It's sort of that thing where you basically identify that it's less than what you want minus some more. So if A is already less than B minus 4, it has to be less than B, right? Yeah. So for example, if 100 is less than 200 minus 4, it has to be less than 200, right? Because it's already less than 196. So guys, interesting concept, right? But that's how you apply it. A little bit of algebra, a little bit of inequalities. Hope that was okay. Like the video, subscribe to the channel, guys. I'll see you at the next one. Thank you.